Have you ever heard the phrase, to see nothing can travel faster than light, and assumed that means the cosmos has a hard wall at light speed? Here's the twist. In the deepest calculations of galaxy collisions, it looks like the universe may be able to stall a merger before the galaxies even get close enough to finish the job, like a traffic jam that forms while cars are still far away. The culprit isn't a new kind of faster than light force. It's something stranger and more abstract. Dark energy, acting less like a push and more like an ever-expanding background that quietly changes the rules. In this video, we'll follow the path of two galaxies as they spiral inward, then watch that spiral lose momentum, because the place they're trying to reach becomes unreachable, not by speed limits, but by cosmic horizons. And the most unsettling part is that this horizon appears to be moving outward beyond what a merger can overcome. So when astronomers say the dark energy horizon, they're not being poetic. They're describing a real boundary in the future of the universe, one that can decide which structures ever fully come together. Before we talk horizons, we need the usual pre-dark energy picture of mergers. Galaxies grow by feeding on each other. Gravity pulls, orbits decay through tides and dynamical friction. Eventually, two galaxies blend into one, forming new stars, new structures, new histories. This works brilliantly in simulations and in the local universe, where the timescales for collisions are short compared to the cosmic expansion timescale. But the universe is not static. Since the late 1990s, astronomers have observed that distant supernovae are dimmer than expected, implying that the expansion of space is accelerating. That acceleration is attributed to dark energy, often modeled as a smooth component with negative pressure, something that makes large-scale expansion behave like a repulsive force on the biggest distances. In this before framework, gravity wins locally, but dark energy increasingly matters on the largest scales and in the far future. The question that emerges is simple. If gravity is strong enough to bind galaxies, can it also bind their fates against the accelerated expansion that never stops? Now let's dig into the core mechanism. Imagine the universe as a stretching rubber sheet with ink dots that represent galaxies. As the sheet stretches, the dots appear to move apart, not because they're flying through space, but because space itself expands. Gravity tries to reverse that separation by pulling dots together, like two magnets resisting the stretch. In Newtonian terms, you can picture an effective balance between inward attraction and outward cosmic acceleration. But there's a more subtle, general relativistic idea. For an accelerating universe, there are distances beyond which signals or causal influence cannot catch up with the future. The horizon is not merely a limit on what light can do. It's a boundary on what future evolution can bring back into contact. When two galaxies begin far enough apart, dark energy alters their relative motion. Their mutual gravitational pull competes with the background expansion that keeps increasing the physical distance between them. In ordinary mergers, the separation shrinks. In horizon-limited mergers, the separation asymptotically stops shrinking and may even grow, meaning the galaxies never reach the stage where tides and friction can lock them together into a final coalescence. A useful analogy is trying to walk towards someone on a moving walkway that speeds up over time. You can close the gap at first, but if the walkway speed increases sufficiently, you eventually stop gaining ground. You're not prevented by a wall, you just can't change your relative position enough. Here's how the discovery and modeling storyline typically goes. Astronomers and theorists take galaxy merger dynamics, initial velocities, masses, angular momentum, and embed them into an expanding universe with a dark energy component. They ask for a given mass pair and their initial separation. Is there a region of phase space where the system's trajectories remain bound, and a region where they become unbound? It's not just about whether gravity can overcome expansion at one moment. It's about whether it can overcome expansion throughout the entire approach. The key result is the existence of a critical scale linked to the dark energy density. Beyond that scale, dark energy's influence becomes dominant in the equation governing the separation of the galaxies. The effective potential develops a barrier. The galaxies approach, but the dynamics cannot carry them through. They may look like they're heading toward each other. Then they drift into a long, slow dance with an ever-increasing gap. The merger stall happens because the future light cones and the gravitationally relevant trajectories don't intersect in the way required for final coalescence. Dark energy doesn't accelerate one galaxy away like a rocket. It reshapes the global geometry so that the conditions for binding fail to persist. So why does this matter beyond being a fascinating mathematical boundary? First, galaxy mergers are not optional extras for cosmic evolution. They're a major engine for building massive ellipticals, for triggering starbursts and active galactic nuclei, and for distributing heavy elements through feedback. If dark energy can prevent some mergers, then the universe's long-term structure will be less mixed than gravity alone would predict. Instead of all regions gradually coagulating into fewer, larger systems, some structures stay dynamically isolated. That changes predictions for the abundance of the most massive galaxies at late times, and it affects how we interpret deep field observations of galaxy populations across cosmic history. Second, this provides a rare observational bridge between an abstract component, dark energy, and concrete fate of structure questions. Dark energy was inferred indirectly from supernova brightness and other cosmological probes. A horizon stalling mechanism offers a way to test whether the acceleration behaves like the simplest models. Finally, it reminds us that faster than light is not the right mental frame. The universe can enforce limits through horizons and global expansion without violating relativity. The cosmic boundary is gentler than a wall, but it's no less real. In other words, the story becomes gravity organizes matter, but dark energy organizes the stage on which gravity operates. Locally, mergers still happen because the gravitational clock runs faster than the expansion clock. Farther out, and especially in the far future, the expansion wins the timing. Two galaxies can start with enough pull to narrow their separation, yet still end up trapped in an approach that never becomes union. And the dark energy horizon is the mathematical expression of that timing failure, a point where the universe's accelerated geometry makes final contact impossible. We're left with an unsettling but clarifying picture. The cosmos doesn't just contain objects. It contains limits on which interactions can complete. Not every gravitational promise is fulfilled because the horizon rewrites the future. If you want to keep following how we turn these deep ideas into testable consequences, subscribe for more, and let's keep looking at the universe's invisible boundaries.